welcome everybody to the course on machine learning, dynamic optimization, and reinforcement learning. We are quite happy that so many are attending here. You're really invited to switch on your, not the microphone, but the camera. So it's, I think it's better if we can see you and you can see us as well. Great. So I can understand if the internet connection is not stable enough that you prefer to switch that off, but otherwise I think it's quite a good idea if you are able to see some of the other people. All right, so my name is Mark Triede and I'm one of the organizers of this course, and we are three altogether, and I just let Jörg and Andreas introduce themselves now.
Andreas, go ahead.
All right, thanks. I'm Andreas, currently postdoc at Professor Triede's Institute. I'm very happy to see lots of familiar faces from the Introduction to R courses in here. I will take over most likely end of December, beginning of January with the reinforcement learning part. And I'm going to teach you something, some methods that you can use to learn a value function. We'll see what that is already today, when you cannot use the classical methods, or you don't want to use the classical methods that you will learn about until then. Before we start, I worked with the introduction of Jörg, and I think Jörg's going to begin with a lecture after that directly. I would like to just go briefly about some of the technical and organizational parts of this lecture. So first of all, of course, there will be lots of coding, especially in the after the first third or so of the lecture. So we will you will need to be able to write your own codes. This is a necessity. You can do the course without having much coding experience so far, but you need to get that experience at least in a certain way until then. We are mostly, I think most of you are familiar with R, so I'm seeing lots of faces that I have already seen in the introduction to R. So I would ask you to either install R and RStudio, or you can also work with Julia, and I think Python will work as well, but none of us is really fluent in Python, so you can't, we can't help you that much in Python. Also, in the latest parts of the lecture, we will use, or we will make use of artificial neural networks, and the codes we will use that time are handwritten, and I only have these at hand in Julia and R. So if you want to stick to one of these two languages, it'd be perfect. But I think working with Python might, coding in Python might work as well. Regarding Zoom, I started these sessions will be automatically recorded, and we would like to put them into the LearnWeb after that, so that you can watch the lecture parts of this class afterwards as well. But for exercises, we will switch into breakout sessions, and these, of course, won't be recorded. So you can see the lecture part online at the LearnWeb afterwards, but you can't see the explanations in the exercises online later on. Regarding the breakout sessions, I just wrote you an email yesterday via the newsletter in the LearnWeb and asked you to just send me group constellations that you'd like to have. That would allow you to work with these colleagues or fellow students that you have been working with in the past, if there are any. So you can still do this. I only received a mail from a single group, and I already created that group in the Zoom breakout sessions. The other groups will be randomly assigned today. If we're working in groups, I'm not sure whether we will have the time today to actually have some exercise work, but if we work in groups, they will be then randomly assigned. But especially in the later parts, we cannot or we shouldn't work in randomly assigned groups, but you should have constant groups, because the tasks get longer and more elaborate, so that you need to work on the same codes over a couple of days or a couple of weeks in a constant and fixed group. So whenever you have anybody you want to work with in a group, just send me an email and I will create these groups in the here in Zoom. Additionally to the group, I will also create a channel for each group where you can share your thoughts and share your codes, especially with each other in the channel, and ask questions, because Mark, Jörg, and me will be inside these channels as well. As I said, we will have lots of exercises. We are switching between exercises and lectures every now and then. So there's no specific structure that we have exercises on Thursday and lectures on Tuesday, but as we come along the lecture, we will switch between lecture and exercises. I think that's it for the technical and organizational part. So I'm going to give over to Jörg with an introduction of himself.
Yeah, thank you so much. Thanks for the organizational details. First of all, also a warm welcome from my side. I'm also very happy that so many of you found the way to this lecture. I think still, I think it's the third time that we are doing that. That it's a very valuable set of tools that you learn. Not only valuable in the sense that you learn some things about how to really program things, but also how to see the world in a sense. We'll come to that later on. First of all, some 2 words from my person. My name is Jörg Lingens. I'm working as a lecturer at Professor Löschel's chair, and I usually do theoretical work, or used to do theoretical work, but now I'm a bit more into sometimes into also microeconometric questions that I try to ask and answer, hopefully. So with this background, we some years ago decided whether it, because I did my PhD on basically dynamic economics, we decided whether we should set up this lecture, because there was a gap, we thought, in this respect. And as I said, we started that a test balloon, so to say, nearly 8 years ago or so, and now we are in the 3rd season of the production line, so to say, and I think it's getting better every year. And yeah, I hope that you will also find the things valuable that we are going to explain. So in any case, if you have questions along the way, or things that you would like to have more information upon, or whether things that you I don't know, do not understand, or whether they are badly explained or whatnot, then just do not hesitate. Just drop a line in the chat, or just unmute your microphone. This is possible, right? That people could do that by themselves. Okay, so just unmute and ask. I think everybody of us, so Mark, Andres, and myself, for sure, are very keen on discussing those things, and are very open to questions. So the general idea of this lecture, that everything is self-contained. So we work everything more or less from scratch, but I mean, it could be that along the way we are losing you. Then just give us a brief remark. Okay, so are there any
just very briefly, I think this is a very small course, so maybe it might be a good idea to let everybody introduce themselves before we really start.
Sure. Thanks again for the introduction of everybody. So I mean, this is one of the advantages of those online meetings, that you can nudge people a little bit to get out of their comfort zones, and tell what they where they're at, and what they're expecting. And I think that was quite instructive for me. And as Andres already said, Mark already said, the introduction to R seems to be a game changer. This is good. And also some people said that they heard good things about past courses. I hope we can live up to these expectations. Keep my fingers crossed. But yeah, we're hoping the best, right? Okay, so we're starting with the course of dynamic optimization and reinforcement learning. Basically, the general idea here is that we want to invite you to using a method that is very versatile when it comes to solving problems, that helps you to structure problems, and we also want to show you how to solve those problems, and especially to how to say numerically solve those problems. And okay, so let's first of all talk a little bit. Sorry, I just wanted to jump into the details, but first of all, let us talk a little bit about the general framework. So what is the objective? As I already said, we wanna introduce you to a very versatile method, how to solve problems. The target group is basically, I would say, more or less advanced or ambitious master students and PhD students. The course is basically split up in 2 or 3 parts. So in part 1, which will be my part more or less, I will give you, or we will give you a basic conceptual notion of how you would solve those problems in a conceptual way. So not really, the goal there is not really finding the solution in the sense, but more to set up, to structure the problem, and to think about how to put it into a structure that could be solvable, right? And then the second step, Andreas and Mark are going to present you methods how to really use these pre-structured problems, put them into the computer and solve them numerically. So what we do not do here is we won't do, and this is, I cannot do that. I'm totally frank about that. We cannot give you a really thorough, rigorously mathematical foundations of everything that we are doing here. So what I can give you and what we will provide you with is some general notion, some general idea, which I think is super helpful, but very do not expect very deep proof of existence and proof of theorems and very detailed the detailed mathematical nitty-gritty stuff. This is definitely not what we are doing here. Andreas already told that lectures and exercises are bundled basically, so we move along a little bit with the lectures and then and when have exercises. Location Stadtrahmen 3, this is obsolete obviously, so for the time being we're in the Zoom meeting room. We're meeting Tuesdays, you are here, so you know that, and Thursdays 10 to 12. And as for the say second part of the semester, we will be heavily using a numerical methods. It would be helpful to for you having installed R and RStudio, obviously, so that you can follow what we do, and also implement the exercise, or do the exercises basically. Okay, Zoom, we talked about that. Okay, one thing that is for many of you very important. So let me briefly talk about how the exam will be done. So we think having a sitting exam of 1 hour and 1.5 hours is not very helpful to see whether you learned something here in this course. This is due to the fact that the course is not about facts and figures that you just have to replicate, but it's more about a craft that you have to learn, and that you have to train, and hence we think this 1.5 hour format, or 1 hour, or even 2 hour format is not a good idea. So what we did up to the last cycles is that people got a take-home exam, and they had 1 week to solve the exam. So basically, it was an extended exercise, and people had to had to structure the problem and solve it numerically, and then afterwards, after this week, present this to us in a 30 minutes frame. Master students have to work on their own because they receive a specific grade or for their job. I think for PhDs it's only pass or fail, right? So they can work in smaller teams, and the exam date is usually after the regular examination period, so that you have enough time to say get rid of the standard exams that you have to sit, that you want to sit, and then work on this thing. Now we are in a situation that we have maybe the 6 times the number of attendance that we had in the past. So we will see how we cope with that in this examination. But I think still it will be the case that we have this, say, maybe for you non-standard format to test what you learned. And I think this is also the more or less the only way, or the only route to go, to have longer time and where you have to or where you can try things and experiment with what you are doing. Okay, but if you have any questions to the how the exam is done or organized, just drop us again a line, and I think it will become clearer as as time goes by, and as we see how many people are really interested in getting a grade or sitting the exam. Okay, so basically we provide you with a relatively detailed slide deck, I would say, which is more or less due to the fact that we didn't follow one of the many textbooks on that dynamic optimization and reinforcement learning. This does not mean that we think that the textbooks are not good enough, but some of them are very focused. Sometimes focus on very specific topics that we did not consider explicitly here. For example, the recursive macro theory is a very I think 1,000 pages Bible on everything macro theory, which is awesome and good to know. But as this course is more about concepts and techniques, we didn't want to look into that in too much detail. If you're interested, you can look this up. The 2 Sargent books, they are both very well written. The Sciostat book on stochastic control is also worth a look, but again, it's very much focused on only stochastic control, not necessarily so much on dynamic optimization, and also not necessarily so much on reinforcement learning. And the book by Sutton is due to their computer science background, is very much focused on the implementation and programming side, and maybe not so much on the conceptual side. Whether this is a good or a bad thing, I'm not totally sure how to judge that. I personally always think that having a good theoretical concept is super helpful, instead of just falling into operative doing. But sometimes it could also be a hurdle. Sometimes operative doing is also a way forward. So this is, I think, a little bit type dependent, so to say. We do not necessarily strictly follow one of those textbooks, but you can find additional information and additional models and additional approaches maybe also there. If you're interested, I suggest you to just have a brief look. Okay, what is the general outline of the course? This is a little bit what I've tried to do some 5 minutes ago or so. So first of all, we present you with a new method, right, and a new way to solve problems, or maybe not a new way to solve problems, but a way to solve new problems, then usually we should motivate why this is important, right? So it would be great to have some idea of why these new problems are of great importance for understanding the real world, for example, or to understand how people behave. This is what I'm trying to do today. So I try to pitch a little bit why learning those things is very helpful. We will then afterwards start with a very simple example of dynamic optimization in a deterministic case. So I will explain you very briefly what is hopefully the difference between the optimization techniques and solutions and methods you already know is compared to the deterministic case. And then we move on and extend the deterministic case to take more realistic settings into account. This is specifically a stochastic environment, okay? And using this, we will also learn how to solve deterministic and stochastic dynamic optimization problems numerically. So how to put the structure that we derive, how to put this structure into the computer and find a solution, hopefully. And afterwards, we will use basically a different method of say a different numerical approach, so to say, to solve those problems. Although the problem structure is basically the same as before. So it is very important, as always, that you be very aware what the general structure of the problem is, because once you know that, everything else are just variations of this general theme. Okay, and this is very important that you really closely pay attention. Usually we had in the past years then applications. So we have basically the lecture consists of the conceptual and numerical things. Then we have exercises, and which are focused obviously on the concepts, on the numerical solutions, not so much on economic applications. In past years, we also discussed some of those more economic applications, but it's not necessarily the case that we will cover that, especially since this year we have 2 weeks less due to the corona situations. But we will see how this works out. Obviously, we have applications in the exercises, right? So what this really means is more economically interesting applications that we had, not so much applications that are just, you know, for you to get a handle on how to operative work on those things. Okay. Right. So are there any questions up to now? Because then I would just move directly into the pitch, why we think that this is an important and a helpful way to extend your toolbox and to extend the way you think about behavior and choices. again, at any point in time, just feel free to interrupt me. Okay, so this is no, there's no hassle when you do so. Okay, let's jump right in. So you're studying economics, right? And the standard idea of what we are doing here, and this is, I think, more or less irrespectively true of which topic in economics you focus on, whether you have macro, micro, whether you have health economics, education, whatnot. The common thread is always that you want to analyze some kind of a choice or a decision problem. Okay, so usually we think that we want to describe how an agent maximizes or minimizes, chooses optimally something to fulfill some objective. Okay, and at the same time, he or she faces some restrictions in reaching this objective. Okay, and usually what you've done so far, I would say in maybe 80% of all the cases of all the decision problems that you encountered so far, is you thought about problems that are static in nature. So the basic idea was there that you have a decision maker, a household, a firm, whoever makes the decision, okay? And the decision maker only makes one contemporaneous decision, so one decision now, basically without considering any time dimension. Making this contemporaneous decision would yield directly into a contemporaneous reward, into a direct reward. Okay, so the idea, for example, as you might know from the beginning of your bachelor studies, think about the standard consumption choice problem, where you are asked, okay, I give you $50 and you choose the optimal, I don't know, pizza and beer bundle. And there your task was to determine how much beer to buy and how much pizza to buy, and to determine from which parameters determine this choice. Okay, and this is basically the static problem, right? So you just consider this initial moment, this moment right now. You have $50, you spend them now on pizza and beer, and now pizza and beer materialize, and you gain some utility from consuming pizza and beer. Okay, so the choice that you were after is basically a number, right? We wanted to know, given the vector of exogenous variables, of income, your preferences, the prices. I wanted to know how much beer and how much pizza would you buy. Okay, and this is just a number, right? And maybe some of you felt a little dissatisfied and said, okay, but in reality, we do not only live in one period, right? But we live in for hopefully many periods, and maybe the lecturer there or the professor there told you, yeah, that's true, but you could just consider one contemporaneous choice after another contemporaneous choice, and so on. So you could just add basically those choices and have choices over subsequent periods. So I choose today how much pizza and beer, tomorrow how much pizza and beer, and so on. But still, the general choice remains static, right? And why is that the case? Well, because in the standard problems, or in the very simplified problems that you were presented, there is no, by and large, in most of the problems, there's no intertemporal effect. Okay, intertemporal externality. It's not really an externality, but it's, you do not have any intertemporal any intertemporal relations, right? Because everything you do today in the static problem does not affect your situation in subsequent periods. So I give you today 50 euro, you choose pizza and beer, and tomorrow I give you again 50 euro, and then you choose, I don't know, tomatoes and bread. Okay, and those two periods are totally distinct. Okay, there's no overlap between them, and there's also the choices that they do not affect the other periods. As a first approach, that might be a good idea, right? Especially if you want to understand in a very simplified way how, for example, demand for goods works. Okay, then maybe the assumption of having the static problem is not too bad after all, because the general structure, the stylized structure is or learning the stylized structure is relatively helpful. But the thing is, in real world choice situations, in many real world choice situations, maybe even in nearly all real world choice situations, this is a very bad description of what people do. And the reason is that in many situations, again, maybe in most situations, everything you do today, every choice you make today has some small or even large intertemporal effect. Okay, so everything we do today usually have in some way or another effects on future possible choices, on future restrictions, on future utilities. But then considering only today, considering only the optimal choice as of today, is not very helpful. Why is that? Well, because the choice you pick today affects the situation you are in tomorrow, but then this affects your optimal choice tomorrow. And the optimal choice tomorrow affects what happens the day after tomorrow, and so on and so on. So if you choose something today, a rational agent would have to think through this possibly very complex notion of what will happen in the future due to my choices. Okay, I don't know, I attend the lecture today and I learn something today, and this helps me tomorrow by doing something, and this is helpful for, I don't know, and this has so many effects that it's very difficult at first glance to structure this problem, to find the optimal solution. But the thing is, again, compared to the static choice, you are not choosing, or you're not after a number, but what you are after is a sequence of numbers. So what you optimally would like to have is an optimal plan that guides you through time, right? This is basically the best thing that you want to have. So in a deterministic world, where many choices have intertemporal effects, you would aim for a plan that tells you what to do at basically every point in time. Okay, you already might think, well, but you know, my life doesn't work that way. That I have a book where I just look it up. Okay, tomorrow is Wednesday, 4th of November. What do I have to do tomorrow? That's true, but this is due to the fact that the real world, there are many uncertainties and stochastics. We'll come to that later on. The general structure there is, and this is the beauty of this approach, is very, very similar to this what we're talking about. But in a deterministic world, you would have this book that tells you, okay, today I'm buying this and that amount of pizza and beer. Tomorrow I do this and that. The day after tomorrow I do this and that, and so on. So the optimal choice is basically a sequence of numbers. Okay, it's basically a time series that you pick. Okay, and this time series might be relatively complex. Okay, for example, it could be the case that you want to that you want to refrain from consuming today in order to have more consumption possibilities tomorrow, right? So instead of just thinking, what is the contemporaneous trade-off? So buying a little bit more pizza, I have to refrain from consuming beer. You also, in this intertemporal context, have to take into account all the effects that will happen due to your choice along the road, down the time road, so to say. Okay, and this is very important. I think this is this insight, this reflecting that choices have intertemporal effects, and that this makes the structure of thinking about choices differently is very helpful. Here's some examples. I think when you contemplate a little bit about the general structure, you will see many more examples. These are classical ones. The consumption choice. Okay, so consuming, I already talked a little bit about that. So your choice how much to consume today affects your wealth position tomorrow, which then affects your income, which then affects your consumption choice tomorrow, which then affects your consumption choice the day after tomorrow, and so on and so on and so on. If you study for an exam, okay, so you study today for your exam, and this changes your level of knowledge, and hence the exam success. So studying today enhances your level of knowledge, which then again maybe enhances how much you optimally study tomorrow and the day after tomorrow, and so on and so on. Okay, and specifically, I think many of you can relate to this exam thing, because a strategy that many people pick is obviously that that you have a very say backloaded choice. So you study very little at the beginning, little, and just before the exam you increase your study effort, your study time. And the interesting question is this really optimal? Is it true that people, so to say, intuitively pick the optimal path, or is it not? Okay. The methods that we will discuss would help you to determine when this is the optimal choice and when it's not. When we look at environmental economics, production choices affect the level of pollution. Specifically, when we talk about pollution in a modern context, we're not talking like 70s acid rain thing, but pollution is basically climate change. Okay, so our production choices affect the level of carbon dioxide in the atmosphere. This obviously affects tomorrow's production choices, because the level of carbon in the atmosphere changes things, right? But also, if you go a little bit, if you step a little bit out of the realm of economics, there you have also intertemporal choices as well. This is also, I think, the reason why this is not primarily been invented by economists, but by engineers and computer scientists and other people in science. So one other example would be, suppose you wanna build a plan for a self-driving car. Okay, you have basically the same problem, right? You want to get from A to B. You know where your car is, and the choice that you make when turning the steering wheel, okay, affects where the car is in the next time instant, which might bring you nearer to your target or far away. And you have to think about what would be the best algorithm to find that way. Okay, in a deterministic environment, if you want to go from A to B, with deterministic restrictions, that would be very simple, right? You would have situations, what happens if you, or which restrict the way your car, or the route your car can take, and you would follow optimally somewhat this, or you would find an optimal route given these restrictions. Okay, and there are many other examples. Okay, so hopefully I was able to convince you a little bit that these kind of questions matter, not only in economics but also in many other applications as well. Since we are economists, we mainly focus on economists-like questions, although sometimes then and when we also discuss, say, more general applications. Okay, when you look at those let me check the time real quick. When you look at those at the structure of those problems, then you may wonder, and you may see that there's a common structure in those problems. You have always a thing, a variable that you could affect instantaneously. Okay, in the consumption choice problem, that would be how much you consume. This is a thing that you can choose. Okay, and there's another variable that explains you, or that characterizes the situation you are in. In the consumption example, this was the amount of wealth that you have. So you have today's wealth, you have tomorrow's wealth, you have the day after tomorrow's wealth, and the idea is that there's a variable that you can choose or control that affects, on the one hand, how you reach your goal, how you feel, but on the other hand also affects the situation you are in. Again, consider the self-driving car. There you also have a variable that you can control. Okay, more or less instantaneously. I mean, not exactly instantaneously, but this is turning the steering wheel. Okay, if you turn the steering wheel to the right, the car moves to the right. If you steer it to the left, the car moves to the left. And you have a variable that tells you the state that the car is in. This is basically the coordinate where the car is. Okay, and where the car is, you cannot choose that. Okay, you cannot say, okay, the car is now at some specific coordinates, and at the same point in time, I want to have that it's at a different coordinate. This is not possible. Same is true with the consumption. You have a wealth of today of, I don't know, 1,000 euro. You cannot pick a situation where this wealth of 1,000 euro magically doubles. Okay, the same is true with the exam thing. Okay, there the variable that describes the situation.
I think we lost Jörg.
The general structure, the common structure between.
Jörg, could you repeat the last 30 seconds?
Yeah, I just got a message that my my internet is not very stable. Did you hear me about talking about the common structure of those problems?
Yeah, we did. It's really just about the last 20 seconds, I'll say.
Okay, so so the general thing here is that those two instances, those two variables that describe your choices, that one of those variables is not adjustable instantaneously. Okay, so as I said, for the level of knowledge, you cannot directly level up your level of knowledge. You cannot choose that. You cannot, just magically say, okay, now I know the double the amount as before. You can double the amount of how much you know, but you have to study, right? You have to do things bit by bit, step by step, and this is a very important distinction, I would say, to think about which situations are adjustable instantaneously and which variables and parameters are controllable, right? Because when you are in a situation, for example, you have to study for this exam and your level of knowledge is fixed, then there's no point in thinking about and pitting yourself why your level of knowledge is so low, and you will there's no way you pass the exam, because the level of knowledge is in this situation at that point in time exogenously given. Okay, so there's a say psychological philosophical message there. When you encounter your state, don't whine about the state. Think about the choice that you can make to change your state. Okay, and this is also the thing that makes the common structure of all those problems. Usually we have two variables. This is you shouldn't take this literally. I mean, it's not two variables. You can have a vector of variables, but two sorts of variables, two kinds of variables. So you have a state variable, and the state variable basically summarizes the current situation. It summarizes the current state, the current situation the decision maker is in, and this is fixed at that point in time. It's fixed contemporaneously. So you cannot, as a decision maker, adjust this instantaneously. Okay, you cannot make the car magically move without time from A to B. This is not possible. If it were possible and you have a method, then just drop me a private mail. Then we have a business model. Okay, in the real world, this is usually not the case. Okay, so these are the state variables. On the other hand, you have control variables, and the control variables, they can be chosen, they can be adjusted from a certain set, given some restriction, and this control variable changes the state variable. So the control variable in increasing your level of knowledge when learning for the exam is obviously the effort you put into learning. So the time and the commitment and everything. You can change that. Okay, you can. This is you can decide upon, and this decision gradually changes the state. Okay, and what we are after. So what would be the optimal? What would be optimal behavior? Optimal behavior would be the sequence of control variables. So basically, the optimal plan that you would like to pursue, which then, on the other hand, also describes the state that you are in. I think with our self-driving car, this is maybe most relatable. So the optimal control would be a plan of in which direction and how strong and everything you would turn the steering wheel. And having this optimal sequence of turning the steering wheel, this then describes the way or the coordinates that your car takes. Okay, or if you have the optimal what we had before with the environmental economics, you want to know the optimal production choices that you pick, and associated to the optimal production choices, you have a level, a state of carbon in the atmosphere. And then you could think about, well, is this really the optimal way to go? And this is relatively complex to find those those controls. I mean, at first glance complex. Once you get a grip, I would say it's not that complex anymore. But at first glance, sometimes people tend to be overwhelmed because everything affects everything, and then it's at first glance relatively complicated to find a solution. But again, I think once we stick very much to the conceptual framework that we are trying to present you and trying to convince you to use, it will be. I mean, it will not be a piece of cake, but it will be easier. Okay, and this is why I think that having a conceptual structure makes problem solving easier. Okay, so a lot of your tasks would be as a first step to really, when you have a problem at hand, to really think hard about what is your state, what is your control, and how do both relate to each other. Okay, in the exercises we will discuss, this is relatively straightforward, because usually we just tell you what the state is and what the control is and how they relate. But I think in real world applications, this would be a huge leap forward once you have this structure at hand. Okay, and what we will do is we will try to review and discuss different solution methods to characterize and solve the dynamic problems. And at the end of the day, the take-home knowledge, I think that you should have is that you are able to identify dynamic decision problems and write and structure them and write them down. And in the second step, at least be able which tools potentially to apply to characterize solutions to these problems. This is sometimes when it comes to finding the solution, but at least you should be able to structure the idea and to know what you would have to do. Okay, this is sometimes more than you could expect in some cases. Okay. Okay.
Yeah.
Do you have questions?
Really, sorry to interrupt. I think that's really one of the important things here to remember at this stage, that we have this fairly simple distinction between state variables and control variables, and we can handle almost any kind of dynamic problem in this setting. So you haven't seen that many dynamic problems yet, but it's really applicable in any area of economics or engineering, as you just said. For instance, if you interact with other people, then what the other people do or think is a state from your perspective, because you can't control how they react directly, instantaneously. But of course, they react to what you are doing, so it's getting a very complicated thing. And since this kind of interaction applies in any area of economics, say marketing or international economics or finance, this kind of problem is really pervasive. And I think it's even harder to think of any area in economics where this is not important, rather than thinking about examples where it is important.
Yeah, I definitely second that. I think this is sometimes it's I mean, when you work with those things, it's sometimes very, very difficult, as Mark already said, to find not only in economics but also in everyday life situations where this way of looking at the problem is not helpful. So I think this is a very versatile tool that you could learn and use. But again, it's this is obviously biased, right? So maybe you wanna consult a third opinion. But I think this is these are great tools. Okay. Are there any questions so far? Okay, then let's move along. As I told you, the general the general setup of all those problems is very much identical, more or less. You have some sort of objective that you want to reach, maximize or minimize or whatnot. You have choices under your control, things that you could change at every point in time, and you have variables that describe the situation that you are in, that describe the state that you are in, which may or may not affect your objective as well. Okay, this is not necessarily the case in, for example, in the consumption choice, for example, where the level of wealth does not enter the utility function. So you're not interested in being rich, you're interested in consuming a lot. But obviously being rich enables you to consume a lot. But you could also think about situations where, for example, consuming a lot and being rich enters your utility function. So again, this is a very flexible way of thinking about those things. And in the first step, what we are going to do is we want to focus on a very I would say simple or standard or archetypal dynamic optimization problem, which is deterministic, and which we will solve by just regular tools that you already know and that you're already familiar with, and which only expand a little bit into the time dimension. But apart from that, those are things that most of you are well aware of, and they're readily applicable, and it's not too difficult to derive using those methods the optimal solution. Okay, so in the first step, we assume that time is discrete. This is, by the way, an assumption that we make all the time. We only focus on discrete time models. All the methods that from a theory point of view, the discrete models are readily extended to continuous time problems. But we refrained. In the past, we also discussed continuous time problems, but we refrained from those because at the end of the day, the computer cannot handle a continuous time. So you have to even continuous problems, you have to make them discrete to solve them numerically. So we just decided, just also in the theory part, just focus on the conceptual part, focus on discrete on discrete time problems. And another specific thing here is that the planning horizon that we consider is fixed. Okay, so it's not an infinite horizon model, but we assume that your task is to make optimal decisions at every point in time, up to the point in time, capital T. Okay, so at all those points in time, the decision maker or the household or the firm or whoever makes the decision controls and chooses the control variable CT. So at any point in time, the control variable CT can be chosen, maybe under some constraints, maybe under some restrictions, or maybe totally unrestricted. We are not. We are very open to that. And the control can be picked at any point in time. So you could pick some control at point in time 2, and at point in time 3, you just pick a totally different control. Okay, this is the same as with the self-driving car. At some point in time, you can just put the steering wheel or turn the steering wheel to the right like a madman, and then the next period you can just turn it to the left like crazy. You can do that. Whether this is optimal, this is obviously debatable, but you could do that, and the same is true here as well. Okay, you can choose your control at every point in time, no matter what the control in the previous period was. So there's no restriction on the control. But what we obviously have is we have the state, which is labeled here by ST, and the state, this is fixed contemporaneously. So at any point in time, I cannot just change the state that I'm in. This is just from me as a decision maker at some point in time t. This is just exogenous. This is just fixed. Future states, so ST+1, they can be affected by choosing things, right? But I know that my choices or my controls affect the state that I'm in the next period in a specific way, namely, and this is governed by a law of motion, namely the effect that I have on the future basically boils down in a functional relation that, given the state that I'm in today, my choice will result in a new state in the next period, in t+1. Okay, and this is a relatively clever way of incorporating this dynamic effects, because obviously it will be the case, even in this very simple law of motion, that obviously my control today not only directly affects the state that I'm in tomorrow, but it also affects the state that I'm in the day after tomorrow, and the day after tomorrow, and the day after tomorrow, and so on. Okay, because the law of motion is a difference equation, right? So if you would like to solve that, or if you were to solve that, you could describe the state that you are in at any point in time as among others, as a function of the control that you pick today. So the challenge, so to say, is to take into account, or to find something, how, or to get a construction where all those possible future effects of the control today somehow are boiled down in one thing. Okay, and we'll see in a minute how this is done in this very simple very simple restricted optimization approach. Okay, so what we want to pick, or what we can pick, is we can pick the path of choices at every point in time where we can make a choice. So this is from 0 to capital T. So for every point in time, there are capital T+1 points in time where I can make a pick. I can choose the control, and at the same time, I also, in a sense, choose indirectly the states, the sequence of the states, because for any plan that I pick, we have directly associated a sequence of states that I follow. Okay, and this is very straightforward. Again, think about the self-driving car. Suppose that you have a plan, a sequence of what you do with your steering wheel. Okay, this is the sequence of the controls. Once you know that, and once you know how the turning of the steering wheel affects the position of your car, you can, for every plan that you pick, describe where your car is. Okay, you can directly describe every point, every coordinate where your car would be. Okay, obviously you need a model that tells you how those two relate, but think for a second that you have this model. Okay, then you could do that. Okay, so what we want to now pick is, or what we are after is, we are looking for the optimal sequence of control variables. But if you have the notion of optimality, obviously you need some you need some valuation. Okay, and what we assume is that there's some valuation function. Economists would call this the utility function. Okay, so a utility function that tells you the reward, basically, of the state that you are in, the control that you picked, and maybe which is also a function of the point in time that you are in. We'll come to that later on. Okay, so you have this utility function, the reward function. It could also be I don't know, in the self-driving car thing, it could be a cost function. Okay, because you want to minimize something, I don't know, where you value the turning of the steering wheel and the state, the coordinates you are in. It could be anything, basically. And what we assume is that the decision maker does not only focus on one contemporaneous reward, but aggregates basically all the rewards over the planning horizon. So in this very simple sense, that the plan that the decision maker wants to pick optimizes, say maximizes, just the sum of the contemporaneous rewards. So this is the reward for every point in time over the planning horizon. Okay, and the reward that you target, or the utility function that you target, is just the sum of all the contemporaneous rewards over the planning horizon. Okay, very, very, very simple, and relatively intuitive, I would say. Okay, you just maximize that. However, as say intuitive as this might seem at first glance, modeling the reward function, the aggregate reward function, in that way is not undisputed. For example, one thing is the rewards between points in time are perfect substitutes. Okay, this is not necessarily what people might consider, and this additive separability. Okay, so that you just have an additive of all the rewards for every period turns out to be important. Why is it important? Well, the idea is very, very simple. If you want to maximize U, okay, this is the sum, then you just can maximize all the parts of the sum. This makes it very easy, right? So this is very important. Again, in many contexts, this seems to be intuitive, okay? But in other contexts, sometimes this turns out to be violated. This is especially true in many situations when you think about the, say, the behavioral things that economists tend to consider. For example, situations where you have time inconsistent discounting, or where you have recursive utilities. So where you have situations where the reward of one period is a function of the reward of the last period, or where you have things like, I don't know, addictive situations, or where you have habit formation, things like that. However, still, for example, in the habit formation situation, you could rewrite then the reward function. Okay, so sometimes it's not such a big deal, because you could just rewrite the structure. Sometimes, as for example with the time inconsistent discounting, it turns out to be of a greater deal, so to say. Another remark that I want to tell you, and a thing that you should focus on, we have assumed that the utility function is directly a function of time, right? So there's no discounting and nothing, and this is due to the fact that we want to keep it very general. The thing, or the question why the contemporaneous reward could be a function of time is, or one interpretation could be that it's time discounting, but we come to that also later on. Okay, so when we want to characterize the optimal path, then we basically, or one intuitive approach, a brute force approach, would be just to maximize this utility function, okay, by picking the optimal control plan and implicitly picking the optimal state variable plan, taking the restrictions that the decision maker has in every period directly into account. Okay, so the first approach would be, and this is called the Lagrange approach, and you will see in a minute that this is very that this turns out to be very familiar, more or less, to the Lagrange optimization that you've seen in many parts of your studies. That you ask, when you start at the beginning of the planning horizon and you are in a specific state as 0, then I choose not only the control, but also the state variables. Now you would say, hey, hold on a second. Didn't you just some 10 minutes ago say that you cannot choose the state variables? Yeah, that's true. What is meant here is basically the future state variables. Okay, remember that you are in 0, and you pick the state variables beginning from the next time period, and this is basically a thing that you could pick. The thing is, those two picks, those two choices in a sense, they are not independent, right? Because they are related to each other via the law of motion, because we know a specific control today gives rise to a specific state tomorrow. So I'm not free to choose anymore. How do I want to consider and build this into the problem? Well, I just could use the law of motion, so the equation that tells me how my control today and my state variable tomorrow are interrelated, and I could use those as as a restriction. Okay. But since I do not have just this restriction for one period, but for every period, okay, what I hence want to do is I want to pick the optimal controls for every time I can pick the optimal control. I want to pick the optimal states for every time I can pick the optimal states. This is basically the future, such that the reward function is maximized. But what I have to take into account is that at every point in time, the choice of tomorrow's state, okay, is restricted somewhat by the choice of today's control. So today's control narrows down which state I could choose tomorrow. Okay, and this is true for every point in time over the planning horizon. So what I basically have is I have one objective function, okay, and I have a constraint, and this constraint holds for every point in time. Okay, so what I basically have is a constraint optimization problem, and constraint optimization problems can be solved using a Lagrange function approach. Okay, in your undergrad studies, you had the utility function maybe, and two choices, pizza and beer, and one restriction. This is basically the same here. The only difference is that you have a lot of variables that you could choose from, and you have a lot of restrictions that you have to obey. Okay, so this is basically a standard maximization problem, but which is very large. Okay, so you have 2 times capital T plus 2 endogenous variables, all the controls and all the future states, and you have T plus 1 restrictions. So this is the restriction that you have to consider every point in time. Okay, why is it 2 times capital T plus 2? Well, you have the controls from 0 to capital T, so from basically today until the end of the planning horizon, and you choose basically or implicitly the states starting from tomorrow, but lasting until capital T plus 1. So capital T plus 1 is basically the state that you leave at the end of the planning horizon. Okay, this is the rest that is left of the state once the planning horizon is closed. We see in a minute or next time that this is relatively important, but that this also makes has a very straightforward economic intuition. Okay, so basically what we have an objective function, and we have a number of restrictions. And what do we do? Well, we set up the Lagrange function, derive first order conditions, and look how far we go. So the Lagrange function is relatively straightforward. So the Lagrange function is just your objective function that you have. So the u, okay, so the u is just defined as this sum. And what you then have is you have to consider the law of motion for every point in time. Okay, so for every point in time, you have to obey to this law of motion. You are restricted. The system is only allowed to evolve according to this equation. Okay, and this is true for every point in time. So starting from 0 to capital T. What you then have to take into account is this is the regular approach in the Lagrange in this Lagrange world, that you have something like a complementary slackness. So what you wanna do is you wanna assume, or you wanna make sure that this expression that you add is zero in any case. So if you stick to your law of motion, well, then it is zero. Okay, and if you do not stick to your law of motion, if this were not binding, well, then this shadow value must be zero. So once the law of motion is binding, you can attach a shadow value, and what this shadow value means, we'll see on Thursday. You can attach a shadow value to this restriction, and this tells you just what or how would you value a situation where you are not restricted to this law of motion. Okay, and what we then do is basically the same as you did in your first, second, third, and so on bachelor semester. We are looking for the first order conditions for every control and every state, and having this at hand, we could then derive the optimal control, so the optimal plan that we want to follow. Okay, and this is a thing with looking at the time that I want to discuss with you next week. No. Sorry. This is the standard plot in my head. Not next week, on Thursday. Do you have any questions so far?
Sorry, I got one question. Okay, so as far as I got it right, the state, so S0 is S0 and T equals 0 is endogenous, right? And from then on,
endogenous is given.
Exogenous, sorry. Right, and from then on, it is dependent on the control, right?
Yeah.
So is it from then on endogenous? Because I got a little bit confused from your sentence that you said when you saying that the control narrows the movements or the possible outcomes of the state.
Yeah.
But does it only narrow it, or does it define it?
No, it does. It defines it. It was not a good. This is
okay.
It was not a good expression. This is
so it was completely endogenous and dependent on the control.
Yeah.
Solely on the control.
Yeah. It nails. Okay, it just nails it down. It just nails it down. And the thing is, but we see later on that obviously once you move into the future states that have been endogenous in the past, then will be exogenous. So once you cannot do anything about it, right? This is like with the car. You start with your car in some situation as 0, then you choose what to do, and at every point where you stop and I ask you, okay, what you are in, you cannot choose, okay, now I want to move the car instantaneously to another coordinate. This is what you cannot do. But at the beginning, where you drive is endogenous and given by the steering of your steering wheel. This is completely correct.
Okay, thanks.
Yeah, I think it's a really good point, because it's in fact in this setting, it's the case that the control completely determines how the future state of the world looks like. This is of course completely unrealistic, and therefore we are going to relax that in the second block of this lecture, because other influences might impact the future state of the world, which from our point of view are usually random. So we are going to include randomness in the law of motion to make the stochastic, the dynamic optimization, stochastic dynamic optimization, but that's going to come later. We start with a simple case because the general structure will already be completely, I hope, completely clear in the deterministic case, and then we will generalize this approach to the stochastic case later on. Yeah, okay.
All right.
I think that's it for today.
So thank you so much. Thanks for having us. Hope you enjoyed a little bit. I mean, as far as one can enjoy those things, a little bit what we talked about. Yeah, and I hope to see you back on Thursday. And again, if there's in the meantime anything, just drop us a line. And have a great rest of the day and a great rest of the week. Thank you so much.